This video is on using second derivatives. To start, let's talk about a theorem that gives us information about how the second derivative affects the graph of the function. So if f double prime of x, right, so the second derivative is greater than 0. So if it is positive, then the graph of f of x, the original function, is what we call concave up. So what I'm really saying here is that if you find the second derivative and you find the places where the second derivative is positive, then the graph that you would see is concave up. Concave up, kind of think of like could hold water. So concave up would be something like this. It's bending upward or something like this. So, you know, you can see that it would hold water if it was like the sides of a bowl. Similar but different if f double prime of x is less than 0, meaning if it's negative, then the graph of f of x, the original function, is what we call concave down. When we say concave down, think of it as bending downward like an upside down bowl. So if the second derivative is negative, the graph will either have this type of shape or this type of shape, concave down. So, you know, the second derivative gives us information about how the graph bends, essentially. It's a rate of change of a rate of change. But, you know, in terms of our actual visual, in terms of the graph that we'll see, it'll help us figure out how to sketch. So, you know, let's take a look at just a couple examples here where we talk about identifying if graphs are increasing or decreasing and if they're concave up or concave down. So we're just going to look at a few examples. So suppose I gave you a graph that had this shape, right? First off, is this graph increasing or decreasing? Well, it's moving downward from left to right, so we know it's decreasing. And is it concave up or concave down? Well, it's concave up because it's like the side of a bowl. It could hold water. So this is concave up. I'll just write it like that for short. So what does that tell us about the first and second derivative? Remember, the first derivative tells you about where a graph is increasing or decreasing. So if the graph here, this is the graph of f of x, an original function, if I say it's decreasing, that tells me that f prime of x, right, the first derivative, well, that's telling me the first derivative is less than 0. It's negative. Because if the graph is decreasing, then the slopes of the tangent lines there would be negative. So f prime of x is less than 0 there. For concave up, that tells me about the second derivative. So the second derivative is based off of concavity. The first is based off of increasing or decreasing. So for the second derivative, since I know this is concave up, I know that the second derivative is positive. That's what we talked about in the definition above. If I did a graph that looked like this, all right, so this is f of x. And let's just talk about it. Is it increasing or decreasing? Well, it's moving upward from left to right, so we know it's increasing. And is this concave up or concave down? Well, it's concave up because it can hold water, right? It bends, so it's able to fill up. So this is concave up. And let's talk about what that tells us about the derivatives. Well, if it's increasing, right, that tells me about the first derivative because the slopes of the tangent lines are going to be positive. So f prime of x is greater than 0. We learned about this in the previous section on first derivatives. For concave up, right, so this is concave up, it can hold water. That tells us about the second derivative. The second derivative, f double prime of x, is also greater than 0. Now we'll look at just a couple more. If I was to say I had a graph f of x that looked like this. Well, from left to right, what is it doing? Well, it's moving upwards, so it's increasing. Is this concave up or concave down? Well, this is concave down because it's like a bowl that's upside down, right? It won't hold water. Talking about how this impacts the derivatives. If it's increasing, right, that tells us the first derivative, f prime of x is greater than 0. In other words, it's positive. And if concave down, that tells us about the second derivative. It tells us the second derivative, f double prime of x, is less than 0. It's negative. And then lastly, if I drew a graph of f of x that looked like this. Well, let's talk about what's happening. From left to right, it's moving downward, so we know it's decreasing. All right, and then what's the concavity? Well, this is concave down, right, because it's like a bowl that's upside down, right? It would not hold water, so concave down. So the graph decreasing tells me about the first derivative. In this case, f prime of x is less than 0 because the first derivative is negative. You have negative slopes to your tangent lines there. Concave down tells us about the second derivative, f double prime of x. Well, that tells us it's less than 0. It's negative. And you know, these are the 4 scenarios you can see that will occur. It's not that you're going to get any other cases in terms of the concavity. Sometimes I like to include this little chart here to help people remember what's going on. So let's talk about, you know, we're going to have a column for f, we're going to have a column for the first derivative f prime, and we're going to have a column for the second derivative f double prime. And a lot of times when I'm working on calculus, I'll draw this for myself first, just so I remember what it is. So let's talk about if f is increasing, right? What's that tell you about f prime? Well, it tells you f prime is positive. If f is decreasing, it tells you that f prime is negative. If f is concave up, well, that's f double prime is positive. And if f is concave down, then we know that f double prime is negative. We can fill in here actually as well. If f double prime is positive, right, we kind of just shift this whole thing over one, right? So f double prime is the derivative of f prime. So if f double prime is positive, it also tells me the graph of f prime would be increasing. For f double prime being negative, it would tell me the graph of f prime is decreasing. Essentially, I'm just shifting this over to these two because f double prime is the derivative of f prime in the same way that f prime is the derivative of f. But if you draw this little table for yourself, a lot of times if you know the first derivative information being positive or negative, or the second derivative being positive or negative, you can work backwards to talk about what's happening to the original function. You should know this. The chart just gives you a handy way of keeping it all together. The next thing we'll talk about here is the second derivative test. The second derivative test actually is talking about another way of finding if a critical value is a maximum or a minimum. So it is not telling you about concavity, at least not directly. All right, so this is called the second derivative test. So it can be used in place of the first derivative test we previously talked about. But it says if f is differentiable, all right, so meaning it has a derivative, and has a critical value, c, such that f prime of c equals 0. So we previously talked about critical values in the last video on the first derivative, but remember critical values occurred when either the first derivative equaled 0 or the first derivative did not exist. In this case, we're saying suppose you have a critical value that you found in a way that it was when the first derivative was equal to 0. Then from there you can make some assumptions from using the second derivative and plugging in that point. So then f of c, the y value, when you sub c into the original function, is a relative minimum. Right, so it's a relative minimum if, and this is what it has to do with the second derivative, if f double prime of c is, and we'll talk about it in a second. So what they're saying is f of c, right, is going to be the y value that you get when you sub c into the original function. But if I find f double prime of c, I'm really trying to see if this is positive or negative. So I haven't finished this statement yet. But if f double prime of c was positive, which is really what this is going to say. So f double prime of c is greater than 0. think about what this means. It means when you sub in the critical value to here, you're going to get a positive value for your second derivative. A positive second derivative tells you you're concave up. If I'm concave up, that my critical value here, right, we know is when the slope is 0, so you know you're going to have right there a relative minimum. Because you're concave up, and that's my critical value, because that's where that slope is 0. That's what this is telling us. That's telling you you're going to have a relative min there. So the reason this comes out to be a relative minimum for second derivative tests, when the second derivative is positive, you're concave up. If you're concave up, then that critical value must be where a minimum occurs, because on the low end. Similarly, say f of c is a relative maximum if f double prime of c, the second derivative, is less than 0. Because we know that f prime of c is equal to 0, so I know the tangent line is going to be flat there. And if I was to look at this, all right, f double prime c being less than 0 tells you, well, we're concave down. Well, what's that look like? Concave down looks like this. If it's concave down, right, and then this is my point, I'm going to have a relative what? Well, it's going up and then coming down. It's going to be a relative max. So it gives you information about the original graph. Sometimes people have a hard time with the second derivative test because they just try to straight memorize it. And you can straight memorize it if you'd like to. Personally, I tend to think about what the second derivative is telling you about the concavity being concave up or concave down, and then determine if it's a max or min, right? If it's concave up, it's going to be a minimum. If it's concave down, it's going to be a maximum. And there's one scenario I haven't talked about here, and that's if f double prime of c equals 0, right? So we have the second derivative greater than 0, we have the second derivative less than 0, and we get information there about being relative max or relative min. But if the second derivative equals 0, then the test is inconclusive. It really doesn't tell you anything. So you should use, I'll say FDT for short, for first derivative test instead. Now when I say that, first derivative test, remember that's where you're using a number line for f prime, the first derivative, and you're determining where f prime is positive or negative on intervals to determine where the original function is increasing or decreasing. So let's do an example here. If we were to say, for example, find all relative extrema, which means relative maxes and relative mins, for f of x equals x to the third power minus 12x minus 1. And we'll do this, try and use the second derivative test because that's what we're talking about in this section. But either way, the way you start this is that you want to find the critical values first. So to find the critical values, remember how this worked. You want to find where f prime of x either was equal to 0 or f prime of x was undefined. So first we need to find f prime of x. And the first derivative here, derivative of x cubed is 3x squared. Derivative of negative 12x is just minus 12. And the derivative of the negative 1 goes to 0, so we got 3x squared minus 12. Now remember, you want where this first derivative either equals 0 or is undefined. Well, it's not going to be undefined anywhere because, you know, this is a continuous function. There are no problem points where you would have, you know, an x in your denominator where it could become undefined. So we're just ready to set it equal to 0 and solve. So we have 3x squared minus 12 equals 0. Well, how do you solve this? You want to factor it. We got 3 times x squared minus 4 if I factor out the GCF of 3. And then remember, x squared minus 4 factors as the difference of squares to x plus 2 times x minus 2. This all still equals 0. And then remember how you solve this. Each factor that has a variable gets set equal to 0. 3 doesn't equal 0. All right, so we don't have to worry about 3. So we say x plus 2 equals 0, x minus 2 equals 0. Solving each of these, here you'd subtract 2 from each side. you get x equals -2. Here we're going to add 2 to each side. You get x equals +2. These are, remember, what we call, right, the critical values. I'll use CV for short. These are the critical values. Now, if you were trying to do this using first derivative test, right, to find the extrema, you would then make a number line for the first derivative and put these on there. But because we found these critical values for when f prime of x equals 0, we can use our second derivative test above, which says if I sub the critical values into the second derivative, I can make some determinations about concavity, which tells me about if it's a max or a min. So that's what we're going to do here. So before we can use the second derivative test, right, and I'll write it here as SDT for second derivative test, just so you know that's the test we're using, you want to find the second derivative. So we need to find f double prime of x. Well, the first derivative is right here, 3x squared minus 12. The derivative of 3x squared, well, that's equal to just 6x. The derivative of -12, well, that's going to be 0. So f double prime is equal to 6x. Now, you don't set this equal to 0 right here. When we're doing second derivative test, what I'm really saying is I found my critical values, and now we want to sub them in. All right, so now sub in the critical values into f double prime of x. And we're doing this because it gives us information. So if I sub these into f double prime of x, let's take a look what happens. So if I had f double prime of the first value I got was -2, this would give me 6 times -2, which equals -12. Now remember, the thing I care about here is the sign on this, right? The sign here is negative, and because this is negative, this tells you that second derivative being negative tells you that the graph is concave how? Well, it's concave down. But if it's concave down, is this going to be a max or a min at -2? Well, concave down looks like this. So that point would go downward, then come back, or go upward, then come back down. So concave down shows you that this is going to be a relative max at x equals -2. Right? Because the first derivative or the second derivative was negative, we knew it was concave down. When we know it's concave down, it means it's going up and coming down because it has to be flat there. That's where f double prime or f prime equals 0. So slope is 0 here. This is concave down because it's negative, so you have a max. If I tried f double prime of +2, my other critical value, right, I would have this is equal to 6 times 2, which equals 12. Well, if this equals 12, what's that telling me? Well, it says that, all right, the second derivative is positive. It means I'm concave up. If I'm concave up, what's that going to be? Well, this is concave up. So concave up would look like this. That point right there, well, that's going to be a relative min. So it's a relative minimum at x equals 2. Now, it's exactly what this said about it being positive or negative above. I just wanted to make sure that you understand that there's a way to kind of reason what this should be rather than just memorize the rule. Right? Second derivative being positive, you know you're concave up. If you're concave up, that point there has to be a minimum. So we know we have a relative max at x equals -2 and a relative minimum at x equals 2. Remember, when you're finding the relative extrema, though, you also need the y-coordinates. So to find the y-coordinates, all right, so now you want to find y-coordinates. And how do you do that? Well, you sub into, right? So by subbing into the original f of x function. Because remember, the y value is actually what the extrema is. The x value is just the point where it occurs. So if I was to look at the original function, I said let's find f of -2 is the first one we found, where we had the relative max. So f of -2, that's going to be equal to substituting into up here, right? The x cubed minus 12x minus 1. So f of -2 would be -2, the quantity cubed, minus 12 times -2, minus 1. And you can calculate this here. This is going to equal, we got -8. -12 times the -2 would be plus 24 minus 1. -8 plus 24 would be 16 minus 1, so this equals 15. So we have a relative, what was it at -2? A relative max. So we have a relative max at x equals -2. The relative max is 15. So the coordinates I'd use is -2, 15. All right, so we've got that part done. And then f of 2, the other critical value, equals 2 cubed minus 12 times 2 minus 1. And what does that equal? Well, we've got 8 minus 24 minus 1. 8 minus 24 would be a -16. Minus 1 is -17. So we have a relative, well, what was it? It was a minimum at x equals 2. So we have a relative minimum at the point 2, -17. Right? The y value is actually what they're asking for. If they just said find the relative max, find the relative min. There doesn't always have to be both. You know, there could be one, there could be the other. You could have multiple maxes or mins depending on the graph. But just realizing that second derivative test gives you another way to find relative extrema. All right, and it's based off the concavity when you sub the critical value into the second derivative. The second derivative also tells us another thing. It tells us about, you know, where concavity changes. So we know it tells us about concavity. The place where concavity changes is called an inflection point. So our next definition here, say an inflection point of a graph is where the function changes concavity. So when I say changes concavity, make sure you know what I mean. You know, what I really am saying is that the graph goes from concave up to concave down, or the graph goes from concave down to concave up. So that's what I mean when I say changes concavity. Where can you find an inflection point? Well, remember, if I'm going from concave up to concave down, it's really telling you about the second derivative. The second derivative would be positive, and then the second derivative would become negative. Or the second derivative would start out being negative, and then the second derivative becomes positive. Well, between those, typically what's going to happen is that the second derivative either has to be 0, or it has to be a place where the second derivative does not exist. So here's our note. This is how you find inflection points. A function has a possible inflection point at C when, right, and C is just an x value, when f double prime of C equals 0, or f double prime of C does not exist. So that's how you know where you can find inflection points. The one thing I want to point out, though, is finding inflection points is not the second derivative test. The second derivative test is a way of finding maxes or mins. To find the inflection point, you do something similar to what you did with the first derivative test, where you create a number line for f double prime in this case, and try to look for where f double prime changes from positive to negative or negative to positive. So in the next example, we'll talk about sketching a graph using all the properties we just talked about. So finding relative extrema, maxes and mins, and also finding the concavity and where it changes, where the possible inflection points could be. So let's take a look at this example here. If I said to sketch the graph of f of x equals negative x cubed plus 3x minus 2. And I'm going to look for relative extrema, and I'm going to look for concavity and where it changes. And before I do any of that, I need to take the first derivative. Because remember, to find relative extrema, I need to use the first derivative to find the critical values. So we have f prime of x is equal to negative x cubed, taking the derivative of that would be negative 3x squared, plus 3x, the derivative of that would be just plus 3, derivative of negative 2, well, that goes to 0. Add the first derivative, remember how you find the critical values, right? So now we're going to find critical values. The critical values, when we do this, are when the first derivative either equals 0 or is undefined. In this case, you know, it's not going to be undefined anywhere, but we got to find where it equals 0. So we'll set the first derivative equal to 0, and we're going to solve this. So you have negative 3x squared plus 3 equals 0. To solve this, you want to factor. I'll factor a GCF of negative 3 out. So I have x squared minus 1 equals 0. Negative 3 times x squared minus 1 equals 0. This factors as negative 3 times x plus 1 times x minus 1 equals 0. From each of these, you want to set each factor that has a variable equal to 0. Remember, negative 3 doesn't equal 0. It's not one of your answers. So x plus 1 equals 0. X minus 1 equals 0. And you want to solve this quickly. Subtract 1 from each side. You get x equals negative 1. Here, I'll add 1 to each side. I get x equals positive 1. So these are, remember, again called the critical values. Right? So we have two of them in this case. There won't always be two. A lot of times, you know, you might have two, but there won't always be two. There could be one, there could be none, there could be three, depending on the polynomial or the function that you're working with. So we found our critical values, and now the next thing you want to do when you're trying to graph is you want to determine if each critical value is a relative, right? Remember when we say relative, it also can be called local. So a relative or local, max or min. Now, it might be neither, right? But this is what we're going to do next in terms of our choices when we go to graph. And you can use either, I'm just going to put this in parentheses underneath it, use either first derivative test or the second derivative test to determine this. Now, because we're in this section, I'll use second derivative test just to make sure we understand how to do it. If I was to use the second derivative test, right, so I'll say SDT, because just showing which test I'm using, what do I need first? Well, I need the second derivative, right? You can't do this without it. So f double prime of x is the derivative of the first derivative. Remember, we have the first derivative above is negative 3x squared plus 3. The derivative here, negative 3x squared, becomes negative 6x. Derivative of 3 goes to 0. So second derivative in this case just negative 6x. And how do you determine if our critical values are maxes or mins? Well, we substitute them into here, right? So we'll sub in the critical values. So we would have f double prime of critical values, or negative 1 is the first one I had, so this would equal negative 6 times negative 1, which equals a positive 6. What do I care about? Well, I care about it being positive, and the reason I care about it being positive is if the second derivative is positive, then I know my graph is concave what? Well, it's concave up. If I'm concave up, what kind of point do I have? Well, concave up, that's a low point, right? So it's a relative min at x equals negative 1. That's what that's showing us. And also f double prime of 1. I'm going to sub in the other value, the other critical value. So negative 6 times 1, well, that equals negative 6. The thing I care about is that it's negative. If that's negative, that tells me that my graph is concave, what? Concave down. If I'm concave down, that tells me that that value I have there is a high point, right? It's going up and coming back down. So this is a relative max at x equals positive 1. So we've identified where the relative min and the relative max occur. And now remember what we want to do with this. Now we take these and we, all right, so now from here we're going to now find the y values, right? So we're going to sub into f of x to find the y values, because that's really where, that's really what the max and mins are when we find these relative maxes and relative mins. So we want f of, right, something in the original function, f of -1. It would equal, substituting in, it would be negative, and then, remember, it's up here. So negative from the function, and then x is -1, so it's negative, and then -1, the quantity cubed, plus 3 times -1 minus 2. Watch your parentheses there, it's really important. A -1 cubed will be a -1, but times a negative makes this a positive 1. So you have 1, and then this would be minus 3, which would be -2 minus 2, that gives me -4. So the coordinates here would be x comma y, -1, -4, and we know at -1 that was a min, so this would be a relative min for that point. For the next point we'll look at, we've got f of 1, right, the other critical value. We're subbing into the original function that we had up here. So we'll have negative, and then it's just 1 getting cubed, plus 3 times 1 minus 2. 1 cubed is 1, negative times a positive makes it a -1, plus 3 will be 2, 2 minus 2, that'll give me 0. That's okay, don't let that throw you off. The coordinates here would be 1 comma 0, x comma y, and that was a relative max, so we have a relative max. So the relative max is 0, right? It occurs at 1, or you could say the relative max at the point 1, 0. And that's good. We found the relative extrema. Now remember, the goal here is to sketch the entire graph, and we want to look at other parts of the graph. So we're going to talk about the inflection point now. And this is the part that we just did a definition of a minute ago. The inflection point, remember, we want to find where the first or the second derivative equals 0, or the second derivative does not exist. So now we'll find inflection points. All right, and we'll write it out here. So to find inflection points, we want to set f double prime of x equal to 0 and solve. Now this is for potential inflection points. You also want to find where it doesn't exist. Well, we already found f double prime. If you didn't use second derivative test here and use first derivative test instead, you would have to find f double prime in this step. But we know what it is, right? So we know f double prime of x is equal to -6x. We want to find where this is undefined or where it equals to 0. It's never undefined, so I don't have to worry about it. Where does it equal 0? Well, how do you solve this? -6x equals 0. You divide by -6 on each side. You end up with x equals 0 divided by a number is just 0. So you get x equals 0. So this is the possible inflection point. You have to check it. Right? So it doesn't automatically become an inflection point. The way we test this is we make a number line for our f double prime. Maybe this pen's dying out. So we make a number line for f double prime of x, and you're going to just put the possible inflection point on there. You put 0, and you're going to test what happens on each side of it. All right, so we test in f double prime, something to the left of 0 and something to the right of 0. Now, we already did this above for the second derivative test when we used these values of -1 and 1. But if you didn't, just showing what you would do, right? So you want to test values, something to the left of 0. I'll say we want f double prime of something to the left of 0. I'll say -1. Well, that ends up being -6 times -1, because f double prime of x is -6x, which makes this 6, which makes it positive. So we know f double prime is positive here. What does that tell me about the original function? Well, it tells me that f is concave how? It's concave up. Now, if you already did this up here, you don't have to necessarily show it again in terms of this work down here. But if you didn't, if you did first derivative test here, you'd want to show this again, because you wouldn't have done it already. F double prime of 1, well, that's equal to a -6 times 1, which makes this -6. The important thing about this is that we got something that's negative. Negative tells you that everywhere to the right of 0, because that's a point to the right of 0, the second derivative is negative. What does that tell you about the original function? Well, it tells you the original function F is concave how? Well, it's concave down. So because this switches from concave up to concave down, right? The concavity changes there. Then we have an inflection point at x equals 0. And what do you want to do? You want to find the y value that goes with that. The y value that goes with it, you would say, let's find f of 0. Substituting that into our original function here, you can see it's going to be negative 0 to the third. It'll just be 0 plus 3 times 0 is 0 minus 2. So f of 0 equals negative 2. Just subbing x equals 0 in the original function. So the ordered pair, and this will be the inflection point, is 0, comma, negative 2. Remember what the inflection point is? It's the point where the concavity changes. So once you've done that, and you found all of these different pieces, we're ready to sketch the graph, right? So f of 0, just in case this got cut off, right? F of 0 equals negative 2 because you were substituting into our original function here. 0 plus 0 minus 2 is just going to give me negative 2 for the y value for the inflection point. So we're going to sketch the graph using the points we have. This inflection point happens to be the y-intercept. If they didn't give you the y-intercept from the inflection point, which doesn't always come out that way, you would have to set x equal to 0 and find y to get the y-intercept. It's not necessarily hard to do, but don't forget to do it. So taking a look at what does this graph look like if I was to sketch it. So I'm going to draw an x and y axis on here. Again, remember this is a sketch. But you should have the key properties that we just talked about. Right? So here's x and here's y. And we'll have, I don't think I have to go much further out than 5 on each side. So we'll go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So taking a look at this, maybe I can add these in here because it looks like it's spread out a bit. Let's plot the points that we know, right, and where they should be. So if I was going to graph this, the first thing I would look at is we found the relative min, the relative max, right? So the relative min was at, let's bring this back up, at negative 1, negative 4. So we have x value negative 1, y value is 1, 2, 3, negative 4. So you would be right there. So that's the relative min. All right, that's negative 1, negative 4. We had a relative max. The relative max was at the point 1, comma 0. So the x value is 1, the y value is 0, so you're right there. So that's the relative max. And then we had an inflection point. The inflection point was at, we said 0, negative 2. So 0, negative 2 would be here. That's the inflection point. And for the y-intercept, well, that's also the y-intercept, right? You set x equals 0, you get y out, so it's already in the same place. Let's talk about how you would graph this. Well, to graph this, to sketch this graph, remember what's going on. At a minimum, it has to be going downward and then coming upward. And we know that everywhere to the left of this, right, that this would have to be going downward because there are no other relative extrema. So we know we're coming downward forever until we hit this point, and then we're going to go back upward. The way it bends is based on this, the concavity. So it's concave up until you get to x equals 0, right? And so I know I'm going to be coming down through here. And I'm not going to worry about the x-intercepts when I do this, just because they're a little more complicated to figure out. But this is a sketch. So relative min, we're coming down to here. Because the relative min, we know it goes down here and then comes back up. We know we're concave up, so we can hold water all the way up until 0, right? That's what the inflection point's telling us. You're always the same concavity. This tells you that concavity is concave up all the way up until 0. Once you get to 0, you become concave down, so it's bending downward. And that's going to be everywhere to the right of 0. Everywhere to the right of 0, it's concave down. So you don't have to worry about changing concavity again. So it should be like an upside down bowl. The relative max here, right? This relative max was at the point 1, 0, just to be complete. You're going to go up to it and then come down. That's what makes it a max. You're going to it and then coming back down. You can't go up past it. The idea behind a max is that you're going to go up to it and then come back down. And remember, this is supposed to be concave down the rest of the way. Arrows on the ends of this because it does go on forever in both directions. And this would be the sketch of f of x that we just did. F of x equals negative x cubed plus 3x minus 2. Now, other questions you might be asked, just to kind of go over them, are intervals where this could be increasing or decreasing, intervals where it's concave up and concave down. Now, we used it all when we graphed it, but if I asked you to state it, make sure you understand what that means. So if I said intervals where f of x is, and we'll do a few different ones. So if I said increasing, well, where is this graph increasing? Well, it's increasing, where is it going upward, in other words? Well, it's from left to right. Well, it's going upward from left to right from the x value of -1 till the x value of 1. And we're only looking at x values, so we're going to give this an interval notation. So f of x is increasing from -1 to 1. You never include endpoints when you're talking about these, because the endpoints, it's neither increasing nor decreasing. If you had done the first derivative test, you would have this information readily available from the number line. Where is it decreasing? Where is it moving downward from left to right? Well, this is decreasing. Looking at this graph from left to right, it's decreasing everywhere up until -1. So that would be from -infinity to -1. Make sure you're using parentheses on both sides. Make sure you talk about this. Not only goes up forever, it goes to the left forever. So it starts at -infinity out to -1. And then it's also decreasing where? Well, the graph is moving downward anywhere after x equals 1, so it's also decreasing from 1 to infinity. You don't usually put a union here because we're not talking about it as a domain. We're just talking about where are the intervals where it's decreasing. Well, it's this one, and it's also this one. You might be asked for the intervals where f of x is concave up. Now, you can get this right away from your number line for the second derivative test. Or you could just look at it, right? Where's this concave up? Well, it's concave up all the way until the inflection point at x equals 0. So from -infinity all the way to the left to 0, right? It's concave up. Where is it concave down? Well, it's concave down everywhere from 0 to the right, right? It's downward everywhere after that. It also shows this on your second derivative number line when you're trying to find the inflection point. So it's concave down from 0 to infinity. Again, you don't include the endpoints on these. So make sure that you understand that. So we can ask you these follow-up questions. Increasing or decreasing, because we use second derivative test, we didn't see it right away here when we did our work. But if you had used first derivative test to find the critical, the relative max and relative mins to determine if they were the critical values, you would have used f prime in a number line there that would have told you where f is increasing or decreasing. So either way, it's okay. We might give you a method to use when we give you a test, just to make sure you know how to use both. But keeping in mind that you're getting the same information. So we'll look at a couple more examples in the next video.